Hello everyone and welcome back. Now, just before this video, we had gone through the first question of the May-June 2023 series paper 2, variant 2, right? So today we will continue on with the second question. So here's part A. State what is meant by the center of gravity of an object. Now we know that the center of gravity is this imaginary point wherein we assume that the object's entire weight is acting through, right? And since this is a 1-mark question, like before, we'll keep our statement brief. So it is a point through which it is assumed that the object's weight, or you could say the object's entire weight, acts through. Entire weight acts through. Right, so that's our first part done and dusted. Now comes the second part. So here we have a larger picture to consider. So let's read this very thoroughly before we go any further. Two blocks are on a horizontal beam that is pivoted at its center of gravity as shown in figure 2.1. That's the pivot right here. A large block of weight 54 newtons is a distance of 0.45 meters from the pivot. So that would be this object that I'm outlining red. A small block of weight 2.4 newtons is a distance of 0.95 meters from the pivot and a distance of 0.35 meters from the right hand end of the beam. So they're talking about this small block now. The right hand end of the beam is connected to the ground by a string that is at an angle of 30 degrees to the horizontal. So we're referring to this tension T here. And the beam is in equilibrium. Now here immediately we should keep in mind that since this is in equilibrium, it's not rotating left or right at all. So all the clockwise moments is equaling all the anti-clockwise moments. So with that in mind, let's go ahead. By taking moments about the pivot, calculate the tension T in the string. So like I just mentioned, since the system is in equilibrium, what that means is that the sum of clockwise moments should equal the sum of anti-clockwise moments. So now it's just a matter of recognizing what moment is being created by the clockwise, in the clockwise direction, and what's in the anti-clockwise direction. So we can see a total of 3 forces over here. Notice that we're not really considering the beam's own weight because it's pivoted at its center of gravity. So even if we did take the weight of the pivot into consideration, it's passing through the pivot and so it's not really creating any moment here or there. So we can effectively ignore the weight of the beam itself. So the other 3 forces we have are the 54 Newton weight, the 2.4 Newton weight, and then the tension T. But notice that the tension T is tilted at an angle of 30 degrees, in which case we can definitely resolve it into its horizontal and vertical components, right? So you can see here, and in fact I'll use a different color to highlight this. Since this is tilted at an angle of 30 degrees, you have one component of tension T that's adjacent to the 30 degree angle, which would be T cos 30. And then one that is perpendicular, let me represent that with a different color, or opposite the angle 30 degrees, which would be T sin 30. Now we can actually, unfortunately, we can ignore the T cos 30 degree component of force. Why, you may ask? Well, if you extend its force arm or its line of action, you'll notice that it's passing through the pivot. When you have such a force that's passing through the pivot, it doesn't really produce a turning effect to begin with. So even though there's definitely this non-zero component of the tension T, it's not really creating any turning effect. So it's creating no moment about the pivot P. And so we can effectively ignore T cos 30. In which case, now we have reduced our situation to 3 scenarios, or 3 forces rather, the 54 Newton, the 2.4 Newton, and then finally T sin 30. So with all of this, now let's separate the ones that are creating an anti-clockwise moment and the ones that are creating a clockwise moment. There's only one force that's creating a clockwise moment, and an anti-clockwise moment, and that is the 54 Newton force. You can see how it's rotating in this anti-clockwise direction. So we can easily calculate its moment in the next slide. Under under the title of anti-clockwise moment. That would just be force times perpendicular distance. In which case, in fact, let's keep it simple and first recognize what the force and perpendicular distance is on this diagram. The force is of course 54 newtons and the perpendicular distance between the pivot and the force is 0.45 meters. So it's just a matter of doing 54 times 0.45 meters and we should get 24.3 Newton meters. So that's your anti-clockwise moment. And now let's calculate the total clockwise moment. Now, when it comes to the total clockwise moments, there are two forces this time. The 2.4 Newton force and then the t sine 30 component. So let's calculate them one by one. For the 2.4 Newton force, we have the force 2.4 and then the perpendicular distance of 0.95. So here we would write 2.4 times 0.95 added to the other force, that is t sine 30. Now this time the perpendicular distance will be between the pivot and the force t sine 30, and then the distance between the two would be 0.95 plus 0.35, which should be equal to, if we simplify things, we get 1.3. So 1.30 meters. That would be the distance between the t sine 30 force and the pivot itself. So here we would write plus t sine 30 times 1.3. So now it's just a matter of equating this with this. So let's simplify things first. We can first simplify 2.4 times 0.95 and we should get 2.28 plus t sine 30 times 1.3, I'll keep that as it is, equals 24.3. I'll keep t sine 30 times 1.3 on one side and simplify 24.3 minus 2.28. And here we will get 22.02. To make t the subject of the formula, which is precisely what we need to find, I can divide both sides by 1.3 times sine 30. So I'd get 0.2 divided by 1.3 times sine 30. So now it's just a matter of plugging everything into your calculator, and what should you get? Let's check. So we know that sine 30 is basically half. So 22.02 divided by 1.3 times 0.5. And now what do we get? We get 22.02 divided by 0.65 and then you will get tension is equal to 33.9 newtons. Right? And so we can definitely round off 33.9 up to 34 newtons. And so that is your final answer. Alright, now let's look at the next part. The string is cut so that the beam is no longer in equilibrium. Calculate the magnitude of the resultant moment about the pivot acting on the beam immediately after the string is cut. So this is where we have to remember that now the beam is no longer in equilibrium and so the total clockwise moment is no longer equal to the total anti-clockwise moment. Now, because the string is cut, we immediately realize that tension is no longer there, which means if we look back at this situation, we basically only really have the 54 Newton force creating its moment and then the 2.4 Newton force creating its moment. We've already calculated what those values are. For the 54 Newton force, it's 24.3 Newton meters. And for the 2.4 Newton force, the moment is 2.28 Newton meters. So because they're in opposite directions, when you want to find out the resultant moment, you would have to subtract them since they're in the opposite directions, right? And so we get 24.3 minus 2.28. And when you plug this in your calculator, you will get 22.02 Newton meters, which you can round off to simply 22 Newton meters. right? Quite straightforward so far. Hence why this was 1 mark, right? Now let's move to the next part. The beam in B rotates when the string is cut and the small block of weight 2.4 newtons is projected through the air. Figure 2.2 shows the last part of the path of the block before it hits the ground at point Y. Now at point X on the path, the block has a speed of 3.4 meters per second. And this speed, now notice that this path is now parabolic in nature. And so when we are told that there's a speed of 3.4 meters per second, it's not going to be horizontal or vertical, but rather it's going to be tangential to the curved path itself. So that's your speed of 3.4 meters per second. And it's at a height of 1.8 meters above the horizontal ground. Air resistance is negligible. So we can immediately recognize some typical concepts that we know of parabolic motion. Now we go to the following. Calculate the decrease in the gravitational potential energy of the block for its movement from X to Y. So when we talk about a decrease in gravitational potential energy, it's occurring due to a decrease in height. And when moving from a decrease in height h. And when moving from X to Y, the decrease in height that's vertical is precisely 1.8 meters. And so that decrease in gravitational potential energy would be equal to basically mgh, but this time it'll be the mass m, gravitational acceleration g times the decrease in height delta h. And now it's just a matter of plugging everything in. Now we can actually make a simplification here. We don't know the mass of this block, but we do know its weight. And we know also that the weight is nothing but mass times gravitational acceleration, right? And so if we go back here, we can basically simplify mg and write it as the weight times the change or decrease in height. And we get 2.4 times the decrease in height, which is 1.8 meters. And what do you get? Let's check. You should basically get times 1.8 and you should get 4.32 joules. Now you could either leave it like this or it's better to round this off to 2 significant figures, in which case you get 4.3 joules, right? So that's your decrease in gravitational potential energy. Now let's go to the next part. Use your answer to C part I and conservation of energy to determine the kinetic energy of the block at Y. Now, the conservation of energy tells us that the total energy of the system doesn't change, meaning whatever total energy the object has at X should equal the total energy at Y. Now, if we go back to our diagram, we can see how at X, the object has not only some velocity, but also some height. So the object at X has kinetic energy and gravitational potential energy. Whereas at Y, there is no vertical height that the object has, meaning there is no gravitational potential energy. So there is nothing but kinetic energy at Y. So I'll write that as Y. And it's this value that we want to find. So it's just a matter of figuring out what the kinetic energy and gravitational potential energy is at X. Now, the kinetic energy would just be half mvx squared and the gravitational potential energy would be mg delta h. And that would be kinetic energy at Y. We have already figured out what the gravitational potential energy at X is. That's going to be 4.32. And then for half mv squared, we can just plug in the numbers. Half times the mass, which in fact we don't know, times the velocity vx squared, which we know is 3.4 squared. Now we don't know the mass of the object and that might pose as a problem, but we can definitely work it out, right? Because we have the weight of the object. Since the weight is mass times gravitational acceleration, I can replace m with the weight of 2.4 divided by 9.81 times 3.4 squared plus 4.32 equals kinetic energy of Y. I repeat, what I've done over here is basically replaced m with the weight of the object divided by the gravitational acceleration. So now it's just a matter of plugging everything into our calculator. And if we do that step by step, let's first find the mass, 2.4 divided by 9.81. That should give you half times 0.24 times 3.4 squared plus 4.32 as it is. Let's simplify things further. In fact, let's simplify the first term more properly. And you will get 1.39 plus 4.32. And now it's just a matter of simplifying things, adding this number to 4.32, and you will get 5.71 joules, which we can round off to 5.7 joules. So that's your final answer, right? Now let's look at part 3. State the variation, if any, in the direction of the acceleration of the block as it moves from x to y. Now, we have to remember that they have given us an assumption that the air resistance is negligible. When we consider this situation, that means there are two consequences. Number one, there is no horizontal acceleration and there is only vertical acceleration. And that vertical acceleration is equal to the gravitational acceleration, which is always pointing downwards. So, as far as the variation goes, there will actually be no variation at all, because the gravitational acceleration stays constant. Here, just mentioning no variation should be enough, since this is just a 1-mark question, right? Now on to the next one. The block passes point x at time tx and arrives at point y at ty. On figure 2.3, sketch a graph to show the variation of the magnitude of the horizontal component of the velocity of the block with time from tx to ty. Numerical values are not required. Now, looking at these kinds of graphical questions might seem very scary at first, but this is actually a trick question, because they're not talking about how velocity is changing, but rather just how the horizontal component of velocity is changing. Now, if we go back to the assumptions we had written out, we said how there is no horizontal acceleration. So let me bring that point back here. When you claim that there is no horizontal acceleration, what you mean to say is that horizontally there is no change in velocity. So there is no change in the horizontal component of velocity I've written as VH. And when VH isn't changing, that basically means VH stays constant throughout the journey. Which means from tx to ty, there will be of course some value of horizontal velocity. Let's label it here arbitrarily, VH, and it's going to stay constant up to the point where it reaches ty. So it will basically be a horizontal line. That's it. Enough for 1 mark. Alright. So this question was basically all about the concept of moments and how you can treat moments in equilibrium, the center of gravity, and then within parabolic motion, we had seen how we can use the conservation of energy to figure out unknown types of energy, and then see how does the horizontal velocity change with time, which in this case, it doesn't. Alright, so now in our next video, we're going to dive into the next third question. Alright, thank you.